Hi everybody. Today we're doing a A2 pure paper from summer of 2014, paper 31. Let's get started. So I did actually do a version of this before, but we had some really bad technical issues. So if you happen to have seen that one, I managed to fix it by charging the graphics tablet pen. So everything should be good, hopefully. Right, so the first question is just about using trigonometric identities. And I think the best approach to emphasize in all of these kind of questions is stick everything in terms of sine and cosine. And then it makes it much more obvious which ones you have to cancel and add together and so on. So in the first one, we need to get everything in terms of sine or cosine of alpha. So we know from the formula booklet that sine of 2 alpha is 2 sine alpha cosine alpha. So that's good, all in sines and cosines. And sec, well, that's just 1 over cosine. Ta-da! 2 sine alpha, no problem. The second one is one of these ones they love, where you're basically actually solving a quadratic equation. Now to see this, we know from the formula booklet that cosine 2 beta is equal to 2 cosine squared beta minus 1. Plug that into that equation there, and you will find you will have to use the formula, so you'll get a quadratic in cosine. So it'll be cosine squared, some cosine, blah, blah. You solve for cosine of beta, not beta itself. And what you'll find is that you get cosine of beta is equal to minus 3/2 or 1/3. Yeah, 2 answers as usual. Now, what you need to do here is recognize, and always check this when you get this kind of result, where it's the cosine or the sine is equal to something. Check that that's an allowed value. So here, if we look at the cosine function, we see, it oscillates between 1 and minus 1. So this is beta, and this is the cosine of beta. So at no point does the cosine of beta get above 1 or below minus 1. Whatever beta is, no matter how big beta is, cosine of beta just oscillates. But this solution is minus 1.5. Well, it's just not allowed. So you will lose a mark if you include both solutions. You need to make clear that you only mean this one solution. And that's all there is to that question. Okay, so now this is integration by substitution. And they've given us what they want us to substitute in, which is very helpful. Sometimes later on you'll have to guess, and that can be very, very frustrating if you make a couple of wrong guesses. So stage 1 of these kind of questions, get du dx. So this is your first step. So in our case, du dx is equal to 3 sec squared x. That is in the formula booklet. The derivative of tan of x is sec squared of x. And then we rearrange this for dx. So dx goes on that side, this comes on this side. It becomes 1/3 du, and then we realize that we're dividing by sec squared of x. And sec squared of x is just 1 over cosine squared of x. So this is just cosine squared of x. Now substitute du, or rather substitute dx into the integral. Do this first. That's absolutely the next thing you should do. Don't try and express everything in the integrand, this bit in the middle, in terms of u. First sub in dx and see if things cancel, like so. So now we have the integral, and the thing on the top is just the square root of u. Well, that's fine. Over cosine squared of x times dx, which is 1/3 cosine squared x du. Yay! The cosines cancel. We don't have to deal with them. So that's fantastic. So we get 1/3 integral u to the 1/2 du. Well, this is no problem for us. We know that that's going to be equal to 1/3 times something u to the 3/2 all times by 2/3. Now, what's happening here? What is happening with the limits? Now, x is being evaluated between x value of 0 and x value of pi over 4. Now, we have to actually change the limits because we're integrating over du. I mean, technically, you could substitute in the value of u, as in 1 plus 3 tan x to the power of 3/2, and then work with the original x limit. So that's perfectly allowed. You will get the correct answer. But why not just, an alternative way is just to change the limits. So the question is, so limits, the question you're asking yourself is, when x is equal to, let's call it x0, so the lower limit, what is u equal to? So, and the same thing, when x is equal to x, I don't know, upper limit, what is u equal to? And so we know when x is equal to 0, well, what is the tan of x equal to? It's also equal to 0. So therefore, the u must be equal to 1 plus 0, which is 1. So the lower limit for u, for the u integral, is 1. What about pi over 4? Well, pi over 4 we can recognize as one of our standard triangles. Okay, pi over 4, that's the 1, 1, square root 2 triangle. With 40, pi over 4 is 45 degrees, so both of these are 45. Well, the tan of 45 is just 1 over 1. So when x is equal to pi over 4, u is equal to 1 plus 3, which is 4. So we're evaluating between the limits of 4 and 1. And if you crunch this out, you'll get the correct answer. Okay. Now, we're looking at a pair of parametric equations. So what is a parametric equation? It is one which is expressed in terms of a parameter, in this case t. So we're kind of used to growing up, from baby school with these kind of y as a function of x. So y is equal to 2x plus 5, for example. And these give things directly. I give the y and the x directly in terms of each other. But an alternative way is to imagine that there is some curve, it could be a straight line, could be like a funky curve, moving through this space. And you are walking along it. And at each second, at each time interval, you know what position you're at. So you know your y coordinate and your x coordinates. You can imagine that there's a kind of a parameter increasing as you move along the curve, say time, for example. That's why we often use t, because we think of it as time. But time increases as I move along this curve. And the y coordinate and the x coordinate are completely determined by what time it is. And this is called the parameter t. So these are parametric equations because they're both expressed in terms of this parameter. You could sometimes, if you really try hard, express it as y in terms of x, but often it's like a massive mess, so don't bother. So we're just looking at them parametrically. And that's actually very easy to work with. So they're asking us for the gradient. Now the gradient is the same old gradient that we're used to, which is dy dx. And here we can just use the chain rule to, so we don't have y in terms of x, we have y in terms of t and x in terms of t. So we're going to use the chain rule to call this dy dt, dt dx. And we must recognize that, so dy dt is on top, dt dx is just 1 over dx dt. So that's actually things we can compute relatively easily. But you should be just a little careful with something like this, it's easy to make really like dumb, simple mistakes. I mean, if you know the quotient rule and the product rule, like you probably won't get it wrong. But just to be sure, so you'll get I'm going to use the product rule version, 3t plus 3 minus 2, 3t plus 2 over 2t plus 3 all squared. So that's our numerator. And then we divide it, and the x one's much more straightforward. It's just 2 over 2t plus 3. Now you're going to juggle this around, you're going to play with it, and it's worth doing it because you get something very simple, which is 5 over 2 all times 2t plus 3. Great. So now they want the gradient of the curve at the point where it crosses the y-axis. Well, when it crosses the y-axis, x is equal to 0. And this will allow us to find the value of t. Like, well, what is the time when I'm crossing the y-axis? Well, we have our, so when x is equal to 0, we have that the natural log of 2t plus 3 is equal to 0. Well, what is the natural, what is this thing saying? It's saying that e raised to that power gives you the thing inside. That's what the logs always say. They say, what do I need to raise the base to get the thing inside? So they're saying that e to the 0, this one is saying that e, because it's base e, is 2t plus 3. Well, what's e to the 0? It's like anything to the 0. Anything raised to the power of 0 is just equal to 1. And that gives us that t is equal to minus 1. So all we need to do is plug that in here. So let's say, let's call this dy dt evaluated at, sorry, dy dx evaluated at t is equal to minus 1. And that just gives us 5 halves. And that's all there is to it. So chain rule, slightly troubling into differentiation, recognizing that you need to find the parameter at x is equal to 0, plugging it in. That's all there is to it. Okay, differential equations. So this is an example of one of them, separation of variables. So this is a separation of variables problem. So if you look at this, separation of variables involves, when you have something that only has 2 variables, say x and y, pushing all the y to one side and all the x to the other. So I'm going to have my y stuff on the left-hand side. And I'm going to be a bit psychic here and only divide by 2y. And you'll see why in a second. So 2y of, dy over 2y is equal to, and then I bring the dx on the other side. There's still a 3 left there, so I get the 3e to the 3x all over 2 plus e to the 3x dx. And now you may be sort of seeing why I left that 3 there. And we're going to, in both cases, we're actually going to refer to this rule, that the integral of f prime of x divided by f of x dx is the natural log of x. So this is the rule for integrating to natural log. You may, of course, be familiar with this case. Now, this is just a specific case of that one. So if you realize that if f of x is just x, then f prime of x is just 1. So actually, this is just a special case. It's the same rule. So here on the left-hand side, we're just going to use the special case. So it's going to be 1 over y. So that's natural log of y is equal to, and we recognize that 3e to the 3x is the derivative of 2 plus e to the 3x. So this must be equal to the natural log of 2 plus e to the 3x. Now we haven't imposed any boundary conditions, so we can't say anything, so it's still an indefinite integral, an antiderivative. So we have to make sure we add the constant here. Now we're given a boundary condition, this thing, and that will allow us to find C. So first, let me express this in a rather suggestive way. I'm going to use the laws of logarithms. I'm going to say that this is the natural log of y to the 1/2. And that's going to be equal to, I'm going to express C as the natural log of e to the c. And you should see that that is the same thing as c, as in the natural log of e, the e's will cancel out. So then I can bring it together, laws of logarithms, with this guy, and call this the natural log of e to the c times 2 plus e to the 3x. Okay, well now I'm going to take the natural log of both sides. I'm going to get that the square root of y is equal to e to the c, 2 plus e to the 3x. And then we're going to square both sides, so I'm going to get that, oh my god, y is equal to e to the 2c. Remember that if I go e to the c all squared, I just multiply the exponents. 2 plus e to the 3x all squared. Now I'm going to put my boundary conditions in, that stuff there. So I'm going to have that 36 is equal to e to the 2c, and when x is equal to 0, e to the 3x is equal to 1. So this is 3 squared. So e to the 2c is equal to 36 over 9, which is equal to 4. So e to the c is equal to 2. And that's it. So you just, wherever you see e to the c here, so you can say, actually, forget even about that. Just put a 4 in here, and that is your equation. So we had to separate variables, and then we had to put in the boundary condition to get the full answer. And you should really memorize. Actually, it might actually be in the formula booklet, but you should know. You should be on the lookout for integrals where the thing on the top is the derivative of the thing on the bottom, and then you'll know to apply the natural log. So you have to spot it yourself, even though it is in the formula booklet. Okay, complex numbers. So they've given us a complex number in Cartesian coordinates. So let me just talk a bit about Cartesian versus polar coordinates in the Argand plane. So the Argand plane is this guy, two-dimensional plane, where the y-axis expresses the imaginary part of some number and the x-axis the real part. So for instance, here I'm going to express the number 2 plus 2i. So it's 2 along the real axis and 2 along the imaginary axis. And the imaginary axis is like, it tells you what number is in front of I. So this is my Cartesian expression. So this is Cartesian expression, like we're used to x and y, of the complex number. But there is another way to express it, and that is using polar coordinates. So every set of coordinates, this is a two-dimensional space. This number has 2 degrees of freedom. It has 2 ways that it can change, 2 important facts about it. Like a vector, you need 2 numbers. So the Cartesian just gives you them in this form. The polar instead will give you another 2 numbers. You always need 2. It will give you an angle, theta, and a radius, r. So if I gave you those 2 numbers, you would still be able to get to the point. I mean, that's the whole idea. I need to be able to give you directions from the origin to the point. So either I can tell you to go east 2 and north 2, or I can tell you to turn around theta and head out r. So how do we translate between these two coordinate systems? Well, you can just use Pythagoras, really. I mean, that's the root of all of this. You have your theta. You can recognize that this height here, this y, which is, the imaginary part, is equal to r sine theta. And this, the real part, the x coordinate, is r cosine theta. So if you want to get r in terms of y and x, well, you recognize that it's just the hypotenuse of a triangle that has sides x and y. So r squared is equal to x squared plus y squared. And what if you wanted to find theta having x and y? Well, you realize that the tan of theta is the opposite of the adjacent, is y over x. So that's no problem. This is how full translation between the two of them. So what about this guy? Well, first of all, you should realize that he needs to be hammered into shape first before you can actually do anything with him, because he's got this imaginary part in the denominator, and we do not want that. We need something in the expression x plus I y, where x and y are real numbers. So what does an I in the denominator mean? We need to get rid of it. So the way to do it is to remember that for a complex number w, so if you haven't seen this notation, this is my expression for w. This is element of, and this is the set of all complex numbers. So why not? Let's sling another bit of set notation in there. Oh, okay. Well, we're going to try. I'm going to use one more symbol because I think it's good to know, and that is, okay, I don't know why it's doing that. Anyway, that's this one, and this means for all. So for all w in the set of complex numbers, w times w star is in the set of real numbers. So this is the complex conjugate. And this is a profound result. So if we have some number w, if we take its complex conjugate and multiply them together, we will get a real number. So what we want to do is multiply the denominator here by its complex conjugate. But we can't just do that willy-nilly. Like, we have to compensate for it. We have to multiply this by something that doesn't actually change its value. So what do I mean? So I'm saying that z is also equal to 9 square root 3 plus 9i over square root 3 minus I times the square root of 3 plus I, which is the complex conjugate of this, divided by the square root of 3 plus I. So now I get to multiply these two denominators and get a real number, but I've compensated for it with the numerator. So this whole thing is just equal to 1, right? So I haven't actually changed z. I'm still allowed to do this. So what do I get? Well, I get 9 times, so on the top, I get 27. You can do this pretty easy yourself. 18 square root 3i minus 9 all over. And then you can recognize that if w is equal to x plus I y, then w star is always equal to x squared plus y squared, because you see that the middle terms cancel out and the last term has a minus sign but also an I squared, because I squared is equal to minus 1. So this thing is just going to be equal to 3 plus 1. So I'm just going to simplify this quickly and say that this is 9/2 1 plus square root 3i. Okay, so good. Now we can actually deal with this guy. I'm just going to drag it and make it a bit smaller so we've got more space. So we have an expression for z, which isn't horrible and full of nastiness in the denominator. So now I'm going to want to express this as in terms of polar coordinates. So I need to extract r, I need to extract theta. So here, I'll just emphasize that my x, if I'm expressing it as x plus iy, my x is 9/2, and my y is 9 square root 3/2. And that's it. So now r squared, also r is the square root of x squared plus y squared. I'll give you 9. And theta is the inverse tan of y over x, which is inverse tan of square root of 3. And you could recognize this as one of your standard triangles, 1, 2, square root 3. And it has to be that one, which is going to be the 60° or the pi over 3. And we're done. So this is our z. So z is equal to 9e to the I pi over 3. And that is the expression in polar coordinates. And that gives all the information that you need to find that point on the Argand plane. So just to emphasize, this is the Argand plane. Right, so now they're asking us to find the roots, the square roots of z. So this is more of a subtle topic. So what does it mean to have, for something to be the square root of something? So we can express that and say, you know, if x, let's say, if x is equal to the square root of y, that's the same thing as saying that x squared is equal to y, right? Okay, this seems super trivial to you, but let me show you what I mean. So I'm taking the n, let's talk in general. Let's say I'm taking the nth root of something. So this is x to the n is equal to y, some number n, some integer. So I'm taking the nth root of a complex number. Well, I'm going to express my complex number in this form. So that's going to be the nth root of r e to the I theta, some complex number. Well, I can separate the r out. The r is just a real number. So I can actually talk about the nth root of r, no problem. But what is the nth root of a complex number? Well, you might think that you could just divide. So let's say I'm talking about this guy now only. So I want an e to the I phi that when raised to the power n is equal to e to the I theta. Now, rules of logarithms, that's the same thing, exponentials, same thing, e to the I phi n is equal to e to the I theta. And so you might just think that phi equal to theta over n is the solution, and it is one of the solutions. But you have to remember that there is a periodicity in these functions. So phi n plus 2 pi is also equal to theta. Sorry, but what I mean is that e to the I, blah, 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 is also equal to e to the I theta. So therefore, phi equal to theta plus 2 pi over n is also a solution. And in fact, in general, phi can be equal to theta plus 2 pi k all over n, where k is equal to 0, 1, and all the way to n minus 1. So why does it stop at n minus 1? Well, when you get to n minus 1, this whole thing becomes theta over n plus 2 pi n over n, which is just 2 pi. So it's theta over n plus 2 pi, which again is, because phi is periodic, just gives you the same result as before. So exactly the same number. Like, the point about these solutions is that is that when you take the nth power, you will get the same answer. But the thing, excuse me, but the thing inside isn't the same. So all these solutions will actually end up being points in Argand plane at regular intervals. But when you raise them to the nth power, you'll always get this guy. Whereas here, if k was equal to n, then it would actually be overlapping. It would have come around all the way here and would be another one. I'm sorry if that's unclear. I'm happy to answer questions, or you can read something, the derivation yourself. But that is the derivation of this formula. So what do we have? We're asking for the second root of z. Well, that's equal to the square root of 9 times the square root of e to the I pi over 3. And so that's just 3. And now we can have several different options. We're looking for a theta between minus pi and pi. So our theta, or rather our phi, I guess, our phi could be equal to pi over 3 plus 0 all over 2, which is pi over 6. So that's one solution. It could also be equal to pi over 3 plus 2 pi all over 2, which is 7 pi over 6. But this is outside of our range, so we have to re-express that. So if you think about it, pi over 6, well, this is this is 6/6 of pi, because it's just pi. And then we've gone a little extra sixth. Well, that's the same thing as going minus 5/6. So it's a completely equivalent. It's the same number. So minus pi over 6. So our two solutions will be 3 e to the I pi over 6, or 3 e to the minus, sorry, 5/6, not 1/6, or minus I 5 pi over 6. Whew. So, and that was it. So that's I think the hardest part there is remembering the logic behind this root formula. If you just, for the exam, if you just memorize it, you can compute it, just do a bit of practice to be sure you get the right answers. If you have some like really high n, so you're asked to take the 6th root or something, you will need to be careful. Remember to look at the range that they're specifying, this range here. They've also specified a range for r, but r is always greater than or equal. Okay, so I guess r could be equal to 0, in which case you've just got a point there. So I guess they've specified that. But yeah, pretty much just be careful of this range of theta. Okay. Right. So we're given this expression full of logarithms, and we're asked to find a quadratic. So all this is really application of the two main rules of logarithms, which is that if you multiply a logarithm by a number, it's the same thing as raising the thing inside to that power. So we're going to do that with this guy, and we're going to do it with this guy. And then remember that if you add two logarithms with the same base together, it's the same thing as just having one logarithm of the things multiplied together. So putting all it all together, what do we have? Well, we have that the natural log of 4x minus 5 squared times x plus 1 is equal to the natural log of 3 to the power 3. Well, now we're just going to take the natural log of both sides. We're going to say that, therefore, 4x minus 5 all squared, x plus 1 is equal to the natural log of 9. Which is equal to 9. Now I'm going to do something which might not be obvious, but it will help us over here. And I'm going to say that we can only do this if this thing does not equal to 0, or less than 0. So this whole, actually, well, you know what? It'll be more clear if I cover it in the second question. So I'll just do it like this for now. But there is actually a small caveat here. And if you multiply this out, you will get this expression. Okay, I'll erase that circle. So now they want us to factorize this. So they're asking us to use the factor theorem, but I think we should use the rational root theorem. And these things are tricky. So if we have a quadratic, no problem. We use our formula, we're laughing. But cubics are pretty much reliant on guesswork. So you have to make a guess, plug that guess of a root into the equation, see if you get 0. If you do, it's a root. And then you sort of need to divide the whole expression by x minus that root. So we'll see how this works. The big trick is getting the initial guess correct. Once you've done the initial guess and then you've crunched through dividing the thing, then you've got a quadratic and then you can find the other two roots, no problem. But getting the original guess. So a little bit of help is given by something called the rational root theorem. And all of these roots you'll be dealing with will be rational roots for these cubic equations. So the rational root theorem says that, and this only works if the root that you're talking about is rational, obviously. So if k is a root, then, oh yeah, and this applies, I'm just going to write this in general, this applies to general polynomials where you have, you know, an x to the n plus an minus 1 x to the n minus 1 plus blah, 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 ending with a1x plus a0. So if k is a root of this thing, then an over k is an integer, and a0 over k is also an integer. So what this means is that the k must be a factor of both an, so in our case 16, and a0, in our case minus 2. Well, in our case, that means that we can only have k being either 1 or 2. So if we try k is equal to 1, and we plug that all in, we get something that is not equal to 0. So it can't be the correct answer. Plugging in k is equal to 2, we do get 0. So this is a root. So here, you know, we might have just started with 1, 2 anyway, but we should also be trying minus 1 and minus 2. But the nice thing is, say your an was 14 and your a0 was 7. Well, you might spend ages going 1, 2, 3, 4, 5, 6, 7. Or you could just know that it has to be factors of both. So you only have to try 1 and 7. So anytime one of these guys is prime, this can really cut down on the time you spend. So, okay, we've got that x minus 2 is one of our brackets. Great. So now we want to find the other two roots. So what we're essentially doing is dividing our full cubic expression. So we have 16x cubed minus 24x squared minus 15x minus 2. And we're dividing the whole thing by x minus 2. So this is like a little tedious, but I'm going to show you how to iterate through it. The point is that you kind of want to, as I've said in previous videos, you kind of want to force some of these things to contain factors of x minus 2 and then mop up the remainder, and you'll find that it will simplify it. So what I'm going to do here is my 16x, I'm going to express as 16x cubed. I'm going to express it as 16x squared times x. And then that x, I'm going to add a little sneaky 2 in. So x minus 2. And then this is obviously going to generate an extra factor of minus 32x squared. So I have to plus 32x squared to compensate. And then just add the rest, which I haven't changed. Well, obviously, this is going to give me 16x x squared, and then that's been divided by the x minus 2 plus 8x squared, and I'm just going to express that as 8x times x minus 2. So this is all going to be over x minus 2. X minus 2 minus 15x minus 2, which is equal to, and now I can take this guy out by cancelling him, so I get 16x squared plus 8x, and oh sorry, I forgot to add plus 16x because I've generated like an extra 16x here. So 16 minus 15 is 1x, so it's plus x minus 2 over x minus 2, and I'm sure you're happy that that's equal to 1. And there we go. Now we've got a quadratic, and it's happily a very easily solved quadratic. So we just get 4x minus 1 all squared, and those are our roots, 4x minus 1 and x plus 1. Sorry, x minus 2. So we're pretty happy that these are the roots of our quadratic equation, as in we factorized it. Now they're asking us to use that to solve this equation. So we might happily just say, oh, well, solution, therefore, for x, it's the same x. We're looking for values of x that will make these things true. So we can say, oh, we've got x is equal to minus 1, and x is equal to, oh, sorry, this is a plus. God, minus 1, I don't know where that came from. X is equal to 2, and x is equal to, yeah, I'm really not sure what it is with this eraser. X is equal to minus a quarter. So these are our two values of x. But be careful, they love doing this. Look at the original equation. If x is equal to 2, then this thing is 8, so we have 8 minus 5, which is 3, and this thing is 2 plus 1, which is 3, and everything's fine, and it will work out. But what if x is equal to minus 1 over 4? Well, in that case, we get that 2 natural log of minus 6 plus blah, blah, blah. Well, what's this? You cannot take the log, any kind of log of x less than 0. So this is not defined. And why is that? Well, the whole thing about logarithms, they're asking that their base, so in this case the base e to the power of what is equal to minus 6? Can you imagine that e to the power of something is equal to, is less than 0? In fact, less than or equal to 0. Well, you can't. I mean, there is no way to make that a negative number if the thing here is an element of the reals. If you have e to the I pi is minus 1, but that's a complex number. That's an imaginary number, and that's acceptable. But if the thing isn't in the exponent is a real number, no matter whether it's positive, negative, fractional, transcendent, or whatever it is, you cannot make it equal less than or equal to 0. So what I'm saying is this solution is not allowed because it gives you the natural log of a negative number, which is illegal. So the only value is x is equal to 2. And that's the only thing that will solve the original equation with all the logs in it. So I hope you're happy with that. Okay. So vectors. So we have a line and a plane. And as I said before, I'm going to use my column notation just to make this a little clearer. I don't understand why anyone would ever use that notation. So our line r is equal to 4 minus 1, 2, plus lambda 2 minus 3, 6. And they're telling us that there is a plane which passes through this point and is perpendicular to the line. So to pass this into like, mathematical mathematical phrasing. I'm going to call this vector W, by the way. This one in front of lambda. So that means that I've got, what I have is my line. I have some origin. And then this vector just gets me onto the line. And then W takes me up and down the line. And lambda controls how far up or down I go. So that would be minus W. And that is our line. So any point R on the line can be reached by first going to the line with the orange vector and then going up and down with W. So if I say that I have a plane which passes through this point and is perpendicular to the line, so there's like a right angle. Well, what I'm saying is that I can get to any point on that plane by first going to that point, this orange point, same as before, and then heading out in a direction that has a vanishing inner product with W. Another way to say that is that W is like is normal to the plane, right? So something that's normal is at right angles, is perpendicular. So W is normal, and we know that if we have an equation of the plane in this form, then A, B, and C define a normal vector to the plane. So there are a couple of ways to do this question. There's a quick way and a transparent way. So depending on your taste, I will show you the quick way. So let's say that W is, so we have that 2. So this is what I mean by saying that W is a normal vector and A, B, and C define a normal vector. So I put in the components where it says A, B, and C. So it's 2x minus 3y plus 6z is equal to some distance d. And now what I need is a point that's on the plane in order to solve for d. Well, I have a point. I know this point is also on the plane and on the line. So I get that 8 plus 3 plus 12 is equal to d, which is equal to 23. So therefore, so my equation on my line is that it's equal to 23. And that's all you need to do. Now, the other way would be to instead think about some vector W that heads out along here, and then you realize it has the dot product vanishes with W, and you solve for those components, but you get the same thing. Ready? Okay, so now we want the perpendicular distance from the origin to the plane. So this is a line which goes from the origin to the plane and meets it perpendicularly, i.e. it's the shortest possible distance from the origin to the plane. So I want a vector, I want to work with a vector that is perpendicular to the plane. Well, I already have one of these, W. Now I'm going to say that there is some other line, let's call it L, and this is a line that goes from the origin, so this is like origin to the plane, and this L, it is some number multiple of W, because I know that W is perpendicular to the plane. So wherever I move W, even if it doesn't have to be where that line is, I could move W here, I could move it there. It's actually going the other way, but whatever. And it would always be perpendicular to the plane. So it will serve my purpose. It will take me from the origin. If I stick its root at the origin and then stretch it until it gets to the plane, it will meet the plane perpendicularly. So it's this line that I want. So this mu is just the stretching factor. Like how much do I shouldn't underline it because that means it's a vector. But how much should I stretch it in order to have it go from the origin to the plane? Well, this is if this is a vector from the origin to the plane, then it also represents a point on the plane. So therefore, it must satisfy the plane equation. So its coordinates are 2 mu minus 3 mu, 6 mu. And I plug that into the equation of P. And I will get, I just plug it all in and I solve it. And I will get that mu must be equal to 23 over 49. So if I want to, so the directionality was given by W, and this tells me how much I need to stretch it to reach just between the origin and the plane. I hope that's clear. So in order to solve the question, we just need the length of that. Well, that's going to be equal to, well, this is going to be equal to x squared plus y squared plus z squared by Pythagoras. And if we plug in this mu and the components that we got, so basically plug the mu in here and work this all out, we get 23 over 7. So that is the distance, the perpendicular distance from the origin to the plane. Okay. So this next one is just a little more subtle, but we can use exactly the same tools we've been using before. So first we can recognize that since the planes are parallel, they have the same normal, like the normal is in the same direction. So we can use W again for our equation. We can basically use this exact equation. 2x minus 3y plus 6z is equal to k, let's say. Now I'm going to talk about a point on this plane Q. And I'm going to say if I want to get to that point, I need to first go to P, go to a point P on the plane P, and then go 14 units up or down along the vector that stretches between them, or let's say W hat. So this is so these planes are parallel. So what do I mean by this W hat? Well, this is a unit vector in the direction of W. So if I have two planes and they're separated by some 14 units, well, then any vector from this one, like the shortest vector to get from there to there, is perpendicular to both, right? So I know that W is perpendicular to both. So W will go from here. If I take that directionality and I scale it so it's exactly 14 units high, then it will stretch just straight above, so straight from one to the other. I need W hat. So W hat is defined as the unit vector version of W. So it's W over divided by the magnitude of W. This makes it into something that is 1 unit in length. So I want to be able to control it by this 14 units so that I will go exactly 14 times 1 units. And it's plus or minus. You don't know which one, you don't know whether Q or P is the top one or the bottom one. So here W is equal to, so the length of W is, so W is square root of 4 plus 9 plus 36, which is equal to 13 square root of 49, which I believe is 7. So this is going to be equal to some point P plus or minus 14 over 7, which is 2 times W, 2 minus 3, 6. And, well, we know, so I'm just going to look for just one specific point on Q. Well, for that, I'm just going to use the specific point on P that I know. So I know that if I plug this point P into this equation, I will get a point on Q. So this gives me that Q is equal to either 8 minus 7, 14, or, because this is plus or minus, or 0, 5. Excuse me, or 0, 5 minus 10. And then all you need to do is, like we did before, plug, this is now a point, these are both points on Q, on the plane Q. So just plug them back into the equation and get your two values of K. And that is the possible equations. That's why I'm saying possible equations. There are two values. Okay, so the next question. We're sketching two graphs. One which has a trigonometric function in it. I'm going to look at the other one first. So let's look at the first equation. So we've got y is equal to, and I'm going to multiply it out, minus x squared plus pi x. Well, this is obviously a parabola. So what can we say about it? Well, we can say that it has when x is equal to 0, y is equal to 0. So the y-intercept is 0. And we can see the x-intercepts are 0 and pi. We see that it's a frowny face because it's got a minus in front of the x squared. And we see that the maximum is given when dy dx is equal to minus 2x plus pi, which is equal to 0, which implies that x is equal to pi over 2. So this is the max. Now, if we, the cosec one, you should probably just memorize it for the exam. But if you're in a rush and you really can't figure it out, then remember that cosec is equal to 1 over sine. So you know that wherever sine gets close to 0, cosec flies off to infinity. And wherever sine goes to 1, cosec is 1. So because 1 over 1. So at 0, at 0, sine is infinity. So you've got to be sort of going up to infinity there. And it's also 0 at pi. So you kind of get this, that is the cosec thing. At pi over 2, sine is 1. So this is equal to, cosec is also equal to 1. But at these points, it flies off to infinity. And then it kind of comes in from infinity and does the same thing there. So that's the cosec function. So if we plot these two together between 0 and pi, which is what they want us to do, let's say pi is over there, and here's pi over 2. There's 1. So here is our cosec function. Exaggerated, but yeah. And what about this guy? Well, we know that it's got a max, it crosses the y-axis here, and it's got a maximum at pi over 2. And when x is equal to pi over 2, y is equal to minus pi squared over 4 plus pi squared over 2, which is pi squared over 4. And that is greater than 1. So we know that the maximum is somewhere here. And that's enough. That's enough to draw it. Like so. So these are our two functions, and we notice that they cross each other. So this is what they're asking for. They're asking you to give all your reasoning, and they cross each other exactly twice. And therefore, there are two real solutions to that set of equations. And I think that's all, yeah, exactly two real roots in this interval. No more, no less. They don't just touch each other. They don't not touch each other at all. They touch each other exactly 2 points. Right, so now they want us to use this knowledge and show that the equation can be written in this form. Actually, we don't really need to use that knowledge, but let's just do it. So this is just manipulating trig identities. So we know already that cosec is 1 over sine, so we have 1 over sine is equal to x pi minus x. So which is pi x minus x squared. We take the x squared over there, and we go 1, and then we take it over the sine, 1 sine x over sine is equal to x pi, and then we just divide by pi, and we get what they want. So that's not a problem. Okay, now this one I'm not going to focus on too much because it is extremely tedious. This is one of those iterative formula questions, and they're using the same. Obviously, it's part of the same question, so they're using this guy to allow you to find where those roots are because they can't be found very easily analytically. So one of these is really just you pick a guess. So pick a guess. You're going to make a reasonable guess based on this. So it's not going to be for the first root. You're going to want to pick something smaller than pi over 2, and then you use that as your xn. Say pi over 2, and then that gives you your xn plus 1, and then you use your xn plus 1 as your xn, and you keep going until the so it says 2 decimal places. So you give each iteration to 4 decimal places. When those 2 decimal places stop changing for a couple of iterations, it means you're probably close enough. So you're going to iterate and bounce around and get closer and closer. So that you only have to find alpha, and then you can actually deduce the value of beta because you know that the whole thing is symmetric. So if that's alpha, then beta is just pi minus alpha. Makes sense? Okay. So this is just a little bit of tedious crunching. Okay. Question 9. So partial fractions. There's a couple of ways to do this. The way I prefer is to say that you have blah, 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 and then you look at the factors, and you divide it into, I'm going to divide it into 2 brackets here. So some people say that this is equal to a over 3 minus x plus b over 1 plus 2x. Oh my God, don't know what happened there. 1 plus 2x plus c over 1 plus 2x squared. And that will give you the answer, but sometimes the denominator will have things that are not so easily factorized. You'll have to deal with an x squared. So I think a much better general rule is to take whatever brackets you have in the denominator, divide them up, and include the powers like that. And then on top, put a general expression like this to an order less than or equal to the one in the denominator. So b plus cx, for example. So the denominator here is order 1. There's just x to the 1. So I put order 0. So the numerator has to have order less than, strictly less than. And here the order is 2 because you will get an x squared out of here. So I go b plus cx, which is everything underneath, below x squared. Okay, so now you just draw this over and you go a 1 plus 2x. I think you can do this yourself. Just be careful because it's easy to make mistakes like here. If you go too fast and try and be too clever and not multiply everything out carefully, you'll probably make a mistake, or at least I do. So just be a bit painstaking, spend the time. It's worth 5 marks. It's worth spending some time on to get the correct answer. So for this one, I will just tell you that in this case, a is equal to 1, b is equal to 1, c is equal to 3. And that works out. The second one, again, it's just kind of tedious. You just use the, you can just use the Taylor expansion, which we've done several times before, that f of x is about equal to f of 0, was actually the Maclaurin expansion, plus f prime of 0x plus 1 over 2 factorial f prime prime. One moment. Sorry about that. Yeah, so f prime prime evaluated at 0, x squared plus plus plus. And here the things we are expanding are the things in the denominator. So you can do it in a bunch of ways, but let's just keep the thing in the numerator, and then we have our expansion of 3 minus x to the minus 1, and our expansion of 1 plus 2x to the minus 2. So you crunch, so that you want things up to the terms in x squared. So for this, you need at least the terms in x squared in both of these, because you could have something where it was just the sort of leading order single number from here and leading order single number from here. So you need an x squared from here, and vice versa for this one. So if you want to account for all the x squared terms, you need to expand both of these up to x squared, and then you just multiply all them together and you get some like horrific polynomial, and just take the terms of x squared and below. So if you get an x cubed, you don't need to worry about writing it, from what they've said. Okay, last question. So question 10, we're given this function and we're told about these stationary points. So you know what a stationary point is. A stationary point is one for which dy dx is equal to 0. So what we can do is just differentiate. We're just asked to differentiate this, so it includes some product and a bit of chain rule, and it shouldn't be too difficult. Just take it slow. So you should get that dy dx is 10 times minus 1/2 sine of 4x plus 4 cosine 4x, all times e to the minus 1/2 x. And this is now equal to 0 for the stationary points. And you recognize that e raised to the power of anything is never 0. So this thing cannot be 0. So this thing inside the bracket must be 0. So we get that if we do that and then rearrange, we get that the tan of 4x is equal to 8. Now we can plug this into our calculator, and that will give us that x is equal to, well, say 20.719 degrees. But we've got to recognize that there is a periodicity in the tangent function. So the tangent function kind of looks like this. But so here is 180, or pi. And this point is also represented here. So if you want, sorry, this is 180. That's 270. So if you want another value, you will have to say 180 plus that. So they're saying they want the values of T1 and T2. So they want the value. Okay, this is difficult, but the thing we're looking at is 4x, not x. So we're looking for 4x. We're looking for x, but the thing that is periodic is the thing that is absolutely inside the tangent function, which is 4x. So we know that the tan of 4x is equal to the tan of 180 plus 4x, and these are both equal to 8. So they'll both satisfy our equation. So 4x plus 180 divided by 4 is also a solution, and this is 65.719. So that gives us our first two. So the only subtlety really here is that it's the 4x that is repeating itself, not the x itself. The x is not periodic in this way. It's the 4x that is, and then you have to divide. So now they're asking us to be super general, and they give us that the x-coordinate of Tn is greater than 25. So you notice that 4x is 180 degrees, or pi, periodic. And actually, well, okay, I may have said that x is not periodic. It is periodic. X is actually 45 degrees, pi over 4, periodic. So x goes from, you know, some x naught plus pi over 4, x naught plus pi over 2, and so on. Now, this they should really have just said to avoid confusion, but 25, this refers to radians, because there is no degree symbol. If it was 25 degrees, then this guy would already be larger. But they're talking about 25 radians. So we want to know that x naught, so the first x, plus n times, actually n minus 1, times, because the n here actually, because it starts from 1, pi over 4 is greater than 25 in radians, obviously. And then actually I should have, well, anyway, the x naught is, and just ask your calculator to do radians, and that's x naught, and that originally gave us the 20.71 whatever degrees. And you solve this, and you will get that n is equal to 33, or you'll get that n is greater than 32.3 or something, and therefore the smallest n is 33. And there we go. Please let me know if you have any questions, and I really hope that was largely clear. Good luck.